Welcome back. Yeah, in the last session I told that I will explain what is the dynamic resistance, and this will be correlated to your exact model of VI characteristics of your PN junction diode. Now if you see, I have drawn already the exact relation or exact VI characteristics using the equation I is equal to I naught into e to the power of V by eta Vt minus 1. Now I have drawn here, maybe if you take forward resistance, because if you take VI characteristics of your PN junction diode, basically the relationship between voltage to current is not linear. Is it linear? No, right? What is linear? The current increases linearly with respect to voltage, but here it is not increasing linearly with respect to voltage. This is what is non-linear curve. When I say this is what is non-linear curve, we should define the resistance in a dynamic way, not static way. Then when you define the resistance in a dynamic way, the dotted line what I have drawn here is nothing but your operating point. About that operating point, what is the change in the voltage and corresponding change in current. Therefore, if you take the ratio delta V divided by delta I, that is nothing but your dynamic resistance under forward bias. But tell me, is this constant? Constant in the sense, remember the value delta V by delta I is not constant, that depends on operating point, right? If that is constant, means dynamic resistance is equal to static resistance. That is nothing but your linear case. Because if you take linear case, right, then if you take the voltage by current or delta V divided by delta I at any point if you define delta V divided by delta I, that will be constant only. When I say this is what your operating point, right, the dotted line is nothing but your operating point. If the curve is linear, then delta V divided by delta I or delta V by delta I at any point, right? This is what is operating point Q1 and then operating point Q2. Let us say at any operating point delta V by delta I, if that is constant, what does it mean? That is linear curve. We know that this is non-linear curve, then delta V by delta I at this point is not same as delta V by delta I at this point, because it is not linear. Therefore, now this is delta V, this is what is delta V, and this is what is delta I, right? Therefore, what I want to say, the dynamic resistance is function of operating point. Whatever or wherever you are operating, let us say this is what is operating point Q1 and this is what is Q2. Mathematically also I can explain. What is the meaning of delta V by delta I or dV by di? That is nothing but slope of a tangent at a given point. At a given point is nothing but operating point. What is slope of the tangent? That is what is delta V by delta I. Now what is slope of the tangent? Therefore, are we having the same slope? No, we are not having the same slope. If you ask me, the slope of the curve at this operating point Q1, which is nothing but the straight line, and what is the slope of the curve at this operating point is nothing but this. Both are having same slope? No, both are not having the same slope. Therefore, our dynamic resistance is function of operating point. Now, that is what is the dynamic resistance. What is our operating point? That is what we need to calculate. Okay. Now, if you ask me how to calculate that mathematically, that is straightforward. We know that. Sometimes in the examination, if this is what is given straightforward, you can take it. Then that is what it is. But the value will change. Depends on operating point. We know that. What is WKT? We know that. Okay. Shortest form, I is equal to I naught into e to the power of V by eta Vt minus 1. Then if you differentiate, that it is di by dV, right? What is di by dV? If I differentiate, this is nothing but, let me call this as equation 1, that I naught into e to the power of V by eta Vt into 1 by eta Vt, differentiation of 1 is 0. Suppose this is what it is, because I naught is constant. Then if you take this, this is nothing but I naught into e to the power of V by eta Vt divided by eta Vt, right? This is nothing but your di by dV. Now can I write this I naught into e to the power of V by eta Vt as 1 implies, call this as equation 2, okay? Call this as equation 2. 1 implies, what is I? I is equal to, can I write it as I is equal to I naught into e to the power of V by eta Vt minus 1. that what is I naught into e to the power of v by eta vt, that is nothing but I, this I naught will come to the left hand side, I is equal to I plus I naught. Therefore 2 implies what is di by dv? Di by dv is equal to I naught into e to the power of v by eta vt minus 1 is nothing but I plus I naught divided by eta vt. Under forward bias, you can take I naught, v is very much smaller than I, therefore your di by dv is nothing but I divided by eta vt. Then what is the forward resistance? Rf is equal to dv by di. This is di by dv. Rf is equal to dv by di. Therefore, what is that value? Which is nothing but eta vt divided by I. This is what is our forward resistance. This is what you can correlate, or this is what you can add. Therefore, I can say then taking some information from the exact model, that is what you are trying to represent as forward resistance, then I can say this is what is our almost practical model, right? But practically this is what is matching to it, even though you are representing with a battery and then resistance. But while solving the problems, very rarely the problems are associated to third approximation. Most of the problems are related to either first approximation or second approximation. Whatever it may be, we should know like different approximations associated to the PN junction diode. Okay, take this. Therefore, the observation is the forward resistance is depending on what? Eta is constant, empirical constant. Vt, that is also constant if temperature is constant, but it is depending on the DC current. Remember, this is AC parameter or dynamic parameter, but that is what is depending on DC point. That is nothing but your operating point. Wherever you are operating, this is nothing but capital I. Wherever you are operating, the resistance is defined. If you operate at this point, the resistance is different. Therefore, different operating points, you'll have different resistances. Different operating points will have different tangential slope. The slope is nothing but 1 by forward resistance. Take this. Am I going fast? I hope all these things are known to you, but the way we are summarizing and then having the observations, finally the conclusion, that is important. That will help you to continue further. Over. Let us take a small example and then try to apply that for different approximations, then we will understand. Now, example circuit is, let us say this is what is 10 volt battery and this is what is 1 kilo ohm and this is what is the PN junction diode. Okay. Now, let us say this is what is the problem. Now, let's see how to solve this. Let us say our ultimate aim is to calculate the current I through the circuit. Okay. Now, let us solve the same circuit using first approximation. Therefore, let us consider first approximation. First approximation. If you use first approximation, what do you mean by that? If diode is in forward bias, then short it. If diode is in reverse bias, open it. Therefore, remember, if this is what is your circuit, if you want to know whether diode is in forward bias or reverse bias, right, to find the status of the diode, there is a technique. The technique is open the diode. The technique is open the diode. Because when you open the diode, right, I'm going to use first approximation only, but the technique to find, therefore, you can write down technique to find, technique, you can follow me, technique to find diode status, diode status, technique to find diode status. Okay. The technique is open the diode. Open the diode. After opening the diode, okay, second point, find voltage across open terminals. Find voltage across open terminals. After finding the voltage across open terminals, then decide if the voltage is greater than or equal to 0. Therefore, use approximate model. Approximate model. Right? Therefore, if I apply the same technique, remember this is very powerful technique, I can say, to solve any problem related to diode. Later on, we are going to see in a given diode circuit, if there are 2 diodes and 3 diodes, how to find the status of diode? You open all the diodes and find voltage across open terminals of all PN junction diodes. Then, based on the approximate model, let us say if I go for first approximation, if the voltage across open terminals greater than 0, short the diode. If the voltage across open terminals less than 0, open the diode. That is what is very easy. But sometimes 90% this is okay, but sometimes we need to see special cases where, for example, there are 3 diodes, then you are opening all the 3 diodes, then you are finding all open terminal voltages of all 3 diodes, then I am saying that if voltage is greater than 0, short, right? But sometimes, let us say diode 1, the open terminal voltage is greater than 0, then if you say short circuit, then maybe diode D2 voltage will change. Those special cases we need to observe. But when we solve the problems, you will understand all those special cases also will be covered. But typically 90% the technique is, if there is a 1 diode, straightforward, no need to think anything, go ahead like this. This is blind technique and then powerful technique. Open the diode, find voltage across open terminals. Then if the voltage across open terminals is greater than 0, less than 0, or greater than V gamma, less than V gamma, we have to use appropriate model based on the problem statement and then go ahead. Okay. Let me apply the same thing here. Right. Now, if you open the diode, therefore to find diode status, I am applying the technique to this problem. Therefore, to find diode status. Okay. Therefore, what is that? Open the diode, right? Open the diode. Now, after opening the diode, I am opening the diode, right? But the diode is still there, but we are not connecting it. Basically, that is the meaning of it. The diode is there, but we are not connecting it. Okay. Before connecting the diode here, what is the voltage it is seeing? Then that is what I want to say. Therefore, this is 1 kilo ohm and this is what is 10 volt. Therefore, now tell me, we opened the diode, then what is the second step? Find voltage across open terminals. Then tell me what is voltage across open terminals? Voltage across open terminals is because when you open the diode, there is no current in the circuit. If there is no current in the circuit, there is no voltage drop across 1K. The entire voltage will come to the open terminals. Therefore, it will have 10 volts. It will have 10 volts. Then tell me, now bring back your diode and connect the diode. When you connect the diode, right, when diode is not connected, it was having 10 volts. The moment when you connect the diode, it is seeing the voltage of 10 volts. Therefore, it needs only the voltage, and the remaining voltage, how much voltage it needs, the remaining voltage will be given to the resistor. And we know that using first approximation, if the voltage across the PN junction diode is greater than 0, short it, right? Therefore, tell me what is voltage across the diode. Before connecting the diode, what is voltage across the diode here? The meaning of voltage across the diode is nothing but this is the one. If that is what is voltage across the diode is greater than 0, yes, greater than 0, short it. Therefore, using first approximation, what is this? Your diode is on, or I can say forward bias. That is in forward bias, because that voltage is greater than or equal to 0. If that is what is the scenario, then what is your circuit? Your circuit is, because we understood the status of diode, right? To find the diode status, we understood the status of diode by opening it and then finding open terminal voltage. Okay. Then we used approximate model. We know that if this is greater than 0, it is short circuit. Therefore, this is nothing but short circuit. And this is 1 kilo ohm, and this is what is 10 volt battery. Now tell me, what is the current? It is straightforward to find, right? Therefore, you can apply. Therefore, what is current? IE is equal to, the 10 volt will come here. 10 volt divided by 1 kilo ohm. Therefore, this is nothing but 10 milliampere. This is what is the current, which is what is flowing through the circuit. That is what is 10 milliampere, and the voltage across the PN junction diode. Therefore, the voltage across the PN junction diode, VD, is equal to 0. That is what is first approximation. And diode is in forward bias. Okay. Take this. Then let's solve the same problem using second approximation. Okay. Maybe this is what is common. This is what is common. This is what is common for all the approximations. Now you can say this is what is case 1 using first approximation. Using first approximation. We are trying to solve the problem using first approximation. Because open the diode, find voltage across open terminals, then use approximate model. What is asked in the problem statement. Therefore, let us say first approximation, when it is on means short circuit. That is what I told in the first approximation. Okay. Take that. Just a minute. over. Now let's see using second approximation. Okay. Now using second approximation. Okay, for the second approximation, the voltage across the diode should be greater than or equal to V gamma. Let us say V gamma is equal to, let V gamma of your PN junction diode is 0.7. Okay, the typical value. Then, is it greater than or equal to 0.7? The voltage across the PN junction diode, before connecting the PN junction diode, the voltage across the PN junction diode is greater than or equal to 0.7? Yes. Then it takes only 0.7. Out of 10 volts, it takes only 0.7. Remaining 9.3 will be given to 1 kilo ohm resistor. I'm just explaining qualitatively, but even though if you do math, you get the same thing, right? But if you take diode out of 10 volts, it is only 0. Means the voltage across the voltage drop across the PN junction is 0. Remaining 10 volts you will see across the 1K. But if you go for second approximation, it takes out of 10 volts, it takes only 0.7. Remaining voltage will be given to 1 kilo ohm resistor. Okay. Then we know the diode is on, that is in forward bias. Then the circuit will be, this is what is 10 volt battery. Then your diode is represented with what? This is what is the diode, right? This is what is the diode. This is the representation, okay? And this is 1 kilo ohm. This is 10 volts. And what is this value? This is what is 0.7. Therefore, now tell me what is the current here? If you apply the current, what is I? I is equal to voltage at this point minus voltage at this point divided by 1K. 10 volts minus 0.7 divided by 1K. What does it mean? What is the voltage drop across the resistor divided by resistance value? That is what it is. Okay. Then we are trying to find the current through resistors. The same current is flowing through the circuit because in loop the current is constant. Right? Therefore, R, I told you, out of 10, 0.7 will be taken by this. Remaining 9.3 will be given to 1 kilo ohm. Both are same. Then you will get 9.3 milliampere. This is what is your current. Maybe if you use first approximation, we are getting 10 milliampere. But if you use second approximation, we are getting 9.3 milliampere. Therefore, actually, maybe if you use exact model, we may get nearer to this. But first approximation, there is some error. Instead of getting 9.3, you are getting 10 milliampere. That error is acceptable. For the same circuit, you are solving using second approximation. Okay, assuming V gamma is 0.7. Now let's solve the same problem using third approximation. Okay. Using third approximation. Right? Then using third approximation, we know that yes, voltage is greater than 10 volts, V gamma, then definitely it is in forward bias. Then if it is in forward bias, what is the model of diode? Diode should be replaced by third approximation. Therefore, your circuit will be like this. Therefore, now your diode is replaced by, this is what is your RF and this is what is your V gamma. Therefore, this is what is your diode now. This is what is your diode. Now this is what is the diode. Okay. This is what is the diode. Okay, and this is 1 kilo ohm and this is 10 volts, and you know already V gamma is 0.7, but what is RF? How to calculate RF? But remember, most of the times the RF will be given in the problem statement. If that is not given, we can calculate because we already calculated, right, from exact model. That is the one, right? We know that what is RF? RF is equal to, we already calculated, which is nothing but eta Vt divided by I. Therefore, when V gamma is 0.7, definitely that is silicon PN junction diode. For silicon PN junction diode, what is eta? Eta is approximately equal to 2. Because nothing is given, we need to calculate on our own. Then definitely you can take eta. If nothing is given, you can take eta 2, right? But remember, in the problem statement, RF will be given straightforward. No need to do all these calculations. If that is what is given straightforward, use it and then calculate. If that is not given, we need to calculate based on the operating point. Okay? Then let's see what is that. Therefore, what is eta? 2. And then what is Vt? Volt equivalent of temperature. Let us consider this as Vt at room temperature. Let us say 26 milli electron volt. Let me take approximately 25 for the easy calculation. 25 millivolt. And then what is I? I is nothing but your bias current. What is your I? You can take it as approximately, you can say your I will be approximately 10 milliampere or 9.3 milliampere or around that. Let me take approximately 10 milliampere. Even if you take 9.3 milliampere, even if you take exact value, that won't change much. You will understand. Maybe for the simplification purpose, 10 or 9.3, close to same. Let me take 10 milliampere. That is what is the current, right? That is what is the current, which is what is flowing through it, right? Then this is what is your 10 milliampere. Then tell me 2 into 25, 50 millivolt divided by 10 milliampere. Then the resistance will be close to 5 ohm. They have taken some approximation, means your I is 10 milliampere, but it may not. Actually, this is 26 and this is 9 point something, 9.3 or 9.2 or whatever it may be. Then you'll get approximately 5 or close to 5, 4.8, 4.7 or 5, 5.1, close to 5. If that is what is 5, let us substitute and then calculate, right? Let's see, what is that? Therefore, if you substitute, then tell me, therefore what is RF? That is what is 5 ohm. Then what is your circuit? Your circuit is nothing but, therefore what is RF? RF is equal to 5 ohm. And what is V gamma? V gamma is equal to 0.7. Then tell me what is the current? I is equal to, therefore I want to know the current. I is equal to, tell me using node analysis, the 10 volts out of 10, 0.7 is taken, 10 minus 0.7. This is nothing but what? The voltage drop across these two terminals. Out of 10 volts, 0.7 voltage is gone here in the battery, then remaining voltage will be dropped across these two, right? Then you can collectively take 1 kilo ohm plus 5k. Therefore, 1 kilo ohm plus 5 ohm. 1 kilo ohm plus 5 ohm. Tell me what is 1 kilo ohm plus 5 ohm? Is 5 ohm significant with respect to 1k? Not. Maybe if you calculate exactly, 10 minus 0.7, 9.3 volt divided by 1k 1000, therefore 1005. Maybe if you calculate, you may get 9.29 milliampere or something. Or I can say 9.3 milliampere only. Okay, this is what is ohm. Therefore, what I want to say, I already told you, even though people call this as practical model, even though this is practical model, therefore the error between third approximation to second approximation is very minimal. Therefore, using second approximation, whatever current we got, which is 9.3 milliampere, almost we are getting the same current. Almost we are getting the same current, even though you consider the forward resistance based on the operating point, which is correlating your exact model. Then we are getting 9.29 milliampere. The error between second approximation to third approximation is so minimum. That is the reason why 90%, if you want to use either second or third approximation, blindly you can go ahead with the second approximation, considering only V gamma. But to solve the problems very easily, on and off, short circuit, open circuit, but that is only for problem solving, which is nothing but first approximation. But in a realistic scenario, in the practical circuits, whatever you are doing in the lab, right, then if you go ahead with second approximation, that is what is good enough to get the results matching, or the practical results will be matched to the theoretical analysis. I hope this is what is clear. Therefore, when to go for it in the examination, if V gamma is given, then definitely have to go with second approximation. And then in the examination saying that take it as ideal model, then you can go ahead with the first approximation. Then I did not see, that's what I'm saying, only 1%, maybe I didn't see any problem till now using third approximation, but rarely, maybe out of GATE 1987 to 2018, if you consider like some 30 years papers, maybe you can see it is very hard to see the problem related to third approximation, but yes, there are problems. Maybe I can say out of 30 years, 1 or 2 problems. Okay, fine. Take this. Remember, this technique is very important because here we are dealing with simply resistor, diode and then voltage. Maybe we are able to understand easily, but as we go on, or when you see the next topic, whatever topics, the chapters I told, the diode applications, right? Then definitely we will have different circuits associated to diode like clippers and clampers. Then we will use the technique to find the status of diode. We should not take static resistance, we should take dynamic resistance because your PN junction diode is non-linear. If PN junction diode is non-linear, the resistance is defined dynamic way. That's why small RF is after derivation di by dV and then differentiation, we got this formula. Okay. You can call this first approximation as level 1, second approximation level 2, third approximation level 3. Maybe if you incorporate so many things like one by one to get all real effects and practical effects with respect to frequency, etc., etc., then the level will increase. As the level is increasing, the accuracy will increase, but the complexity will increase. Right? As the accuracy is increasing, complexity will increase. That is obvious. This is what is related to PN junction diode. Similarly, we need to see, right, the BJT part and the MOSFET part. With that, I can say the fundamental session or the chapter 1, like the concepts on fundamentals, I can say they are over. Then we can start the BJT amplifier section. Okay. Whatever theory we are understanding, try to apply onto the problems. Therefore, we need to solve multiple problems. When you solve multiple problems, then only we will understand theory in a better way. Okay, now write down BJT. I will not explain BJT operation, it needs more time to explain, but whatever I need for analog circuits, I will explain. But I just explained a little bit about PN junction diode and then equivalent circuits, or I can say approximation levels. BJT. If you consider the BJT cross-sectional view, like your PN junction diode, we have 3 terminals and this is what is emitter, base, collector, and emitter is heavily doped. I am taking NPN transistor, base is lightly doped, collector is a typical doping. Okay. Now when I say the meaning of N plus is nothing but it is more than typical doping concentration, P minus lesser than typical doping concentration, N typical doping. That is the meaning of it. I already told you the meaning of typical doping, right? What is that? 10 to the power of 8 is to 1, right? The typical doping is 10 to the power 8 is to 1 or 10 to the power of 10 is to 1, in the order of 10 to the power of 8 to 10 to the power of 10. For every 10 to the power of 8 silicon atoms, one impurity atom will be added. If you try to dope more, let us say 10 to the power of 5 is to 1, like Jena diode, but in the case of Jena diode, both N, P will be heavily doped. But here, not all the terminals or all the materials are heavily doped. No, only emitter is heavily doped. And base is not heavily doped, less than the typical doping. And collector is a typical doping. Okay, maybe the ratios can be defined, but this is what is the typical transistor. When I say typical transistor, not all the like emitter, collector and base are typically doped. Typical transistor means emitter is heavily doped, base is lightly doped, collector is a typical doping. This is what, with these doping concentrations, I can say the BJT is typical. Okay, maybe if you see BC107 transistor which we use in our lab, right? I can say a typical transistor where emitter is heavily doped, base is lightly doped, collector is normal doping. Remember why the people have come up with these doping profiles. If you don't maintain these doping profiles, what will happen, right? Means instead of emitter which is not heavily doped, let us say it is typical doping, then remaining things are full form, means P is P minus and then N is N, but emitter is not heavily doped. Then what will happen? Remember this device, right? If emitter is not heavily doped, you will not get more beta, you will not get more beta, and you will not get alpha close to 1. These are all device operation parameters, and ultimately that is not going to give you voltage gain. Remember, we are going to use your BJT as an amplifier device. Therefore, we want to get more and more gain from your voltage amplifier, or current amplifier, or transconductance amplifier, or transresistance amplifier. Let's see the different types of amplifiers later on. But remember, this plays very important role to get more beta. If you get more beta, more current gain, obviously more voltage gain. Those things we'll see later, but this is what it is. And one more thing, not only doping profiles, the size of the emitter is typical, size of the base is lesser, size of the collector is more. We have to have. Let us say in the interview, if somebody is asking you to explain the BJT operation using cross-sectional view, then if you draw something like this, the moment when you draw like this, wrong. Then immediately the interviewer may say that, wait, let me ask another question. Means he'll understand that this is wrong, because the moment you draw the base width very high, remember you will not get beta, you will not get alpha close to 1, alpha close to 1, beta very much greater than 1. Ultimately we need those parameters to get more voltage gain. First of all current gain and then voltage gain, right? Therefore don't draw like this, because it has significance. But remember, if you increase the base width, what will happen and all, you'll get those things from your device operation. But whatever I need, I'm just explaining. Here, tell me how many PN junctions we have. How many PN junctions we have? I can say this is nothing but one PN junction diode, P and then N, and this is another PN junction diode, P and then N. Therefore, I can say emitter base junction, collector base junction. Therefore, we have two PN junctions for both the junctions, but the base is common, right? What it may be, we have two PN junctions. Therefore, let me call this as emitter base junction, and let me call this as collector base junction. For both the junctions, because base is common, I can call this as simply emitter junction, and I can call this as simply collector junction, because base is common, right? Therefore, I can call it as emitter junction and a collector junction. Now, tell me what are all the possible combinations with respect to biasing. Let us say this is what is your emitter junction and this is your collector junction, right? Now tell me, if emitter junction is in forward bias and collector junction is also forward bias, right? We can apply the voltage across emitter base and we can apply the voltage across collector base such that both are in forward bias. We can apply, or we can see the voltage and we can see the voltage, then if both are in forward bias, right? Let us say if this voltage is greater than or equal to its V gamma, and if this voltage is base to collector, if that voltage is greater than or equal to its V gamma, both are in forward bias. Okay, in that I'm using second approximation. I'm considering the V gamma of both the junctions, right? I'm not going to with ideal model. Okay, you can go ahead with ideal model, but with respect to the practical circuits, going with second approximation, that is what is more than enough. For that we need the cut-in voltage, that is nothing but your V gamma, right? Now, when I say this is what is JE and then JC, when both are in forward bias, right? Then tell me, this is what is called region definition. Then how many possible combinations we have? Definitely we'll have 4 combinations. Either both are in forward bias or both are in reverse bias. This is forward bias, this is reverse bias, this is reverse bias, or this is forward bias. Right? Now, just listen, I'll give you time to write down. If both are in forward bias, this region is called saturation region. This region is called saturation region. Now, case 2, if both are in reverse bias, this region is called cutoff region. This region is called cutoff region. See, in the case of PN junction diode, we have only forward bias, reverse bias. But here we have 2 junctions. Therefore, based on the bias of both the junctions, we are defining the region. Okay, you will get 4 combinations. Therefore, third one, JE is in forward bias, JC is in reverse bias. This is what is called active region. Now the last combination, JE is in reverse bias and the JC is in forward bias. This is what is called inverse active region or reverse active region. This is what is the region. Now let's see the application part. That is what I am going to use. Okay, if you take application part, what is that? When both are in forward bias, right? Saturation, right? Kind of, maybe let me take ideal model to just explain. This is on, this is on. When both are on, then collector to emitter is a kind of short circuit. If you take ideal model, because this is diode, this is also diode. This is short, this is short. Therefore, this is short circuit, right? That is nothing but on switch between collector to emitter. I am just taking between collector to emitter because path is there. When both are on, there is a path. Therefore, that is nothing but on switch. If both are in reverse bias, this is off, this is off. Therefore, this is open, this is open. Between collector to emitter, both are open. There is no connectivity. Therefore, off switch. People define these two. What is the application? Therefore, this is nothing but switch. When I say switch, switch is associated with 2 states, on state, off state. Therefore, on state for saturation region, off state for cutoff region. Therefore, the application is nothing but the switch action. If you biasing is nothing but providing the voltages across the PN junction such that both will be in forward bias, saturation, providing the voltages such that both will be in reverse bias, cutoff. Therefore, on switch, off switch, on switch, off switch. Therefore, if you apply the bias voltages such that you are getting switching action, that is what you see. Remember, in digital circuits like diode transistor logic, RTL logic, TTL logic, ECL logic, all logic families with a transistor, right? Those are all associated to digital circuits. Always the transistor will be switched in between saturation to cutoff, cutoff to saturation. Okay, that is what you can say. Except emitter coupled logic where the transistor will be in active region. But anyway, we don't have the transistor logic families in our syllabus. And we have only CMOS logic families or NMOS or PMOS, but ultimately CMOS logic families. In current industry, everybody is using CMOS logic families. Okay, 95% people are using CMOS logic families. Okay, why? If time permits, we will see all those things later. Now, coming back to active region, JE is in forward bias, JC is in reverse bias. The application of this is nothing but the active region will be used for amplifier. Therefore, whatever introduction part I gave, right, I told BJT amplifiers, if you want to use your BJT as an amplifier, right, that should be in active region. Only when the transistor is in active region, then only we can get amplification, right? Why we get amplification? I will explain with respect to some equivalent representation, then you will understand. Now, coming back to the last one, what is the application of this? Did you hear any time inverse region, inverse active region? Yes, we heard, but is there any application of this? Now, tell me, if both are in forward bias, that is what is called saturation region. If both are in reverse bias, exactly opposite to on switch, that is nothing but off switch. Okay? Forward bias, reverse bias, active region, exactly opposite to it, because forward bias is in the reverse bias is in the forward bias. Therefore, exactly opposite to it. Therefore, what is complementary of amplification? The complementary of amplification is nothing but attenuation. Therefore, we will not get amplification. You will get attenuation if you bias your transistor in inverse active region. Therefore, you will get attenuation. When you get attenuation, therefore, this is what is attenuator. This is what is attenuator. But let me tell you, do you want attenuator from BJT? Do you want attenuator from BJT? If you ask me, no. Reason. Can we get amplification using passive elements? What do you mean by passive elements? You will study from network analysis. Then I think resistor, inductor, capacitor, you can call them as passive elements. Using passive elements, can we get amplification? Amplification is nothing but what? Let me speak with respect to voltage amplification. Remember, when I say amplification, default people say voltage amplification, but specifically you can say current amplification, transconductance amplification, transresistance amplification. Anyway, we will see these types of amplifiers from feedback amplifiers. That is one of the topics which we need to study. Okay, but when I say for the time being, when I say amplifier, default it is voltage amplifier. When I say voltage amplifier, right? When I say voltage amplifier, let us say this is what is my output V0 and this is what is my input Vi. I am representing with small letter. The meaning of small letter is nothing but the signal which is changing with respect to time. Vi, the signal which is changing with respect to time. V0. Right? Because amplification and all, that is realistic signals or AC signals, not a DC signal amplification. We don't want DC signal amplification. We want AC signal amplification. Example, voice signal. I'm speaking continuously, and if you translate that into electrical domain using transducer, which is microphone, then you'll get, if you see that in CRO or some oscilloscope, you'll see the voltage or the signal changing with respect to time, because that is random signal, right? Therefore, definitely that is changing with respect to time. That is what we want. Audio amplifier or video amplifier, depends on the type of signal what you are exciting at the input. Okay, that's fine. For small Vi, small V0, we want gain. But if you want to get gain, can we get gain or can we get amplification using passive elements? Passive elements in the sense using resistor, inductor, capacitor. Can we get it? You say no, right? But let me ask you, if you say no, I'll ask you one question. What is that? Is inductor passive or active? First of all, what is the meaning of passive element and what is the meaning of active element? The meaning of passive element to understand, right? Not the official definition. I'm just giving you the definition which is easy to understand. Passive element is nothing but ultimately the amount of energy what you get from the element to the outside world is zero. Resistor will not give any energy. It will take and then dissipate as heat energy, right? It is a transducer converting electrical energy to heat energy. But it is not delivering any energy to the world. Similarly, inductor, it is taking the energy, but it is not dissipating, again, but it is giving back. That's why that is what is called reactive element. When it is giving back, means it is giving for some period, right? Then it is acting as an active element. But is it what doing continuously throughout the lifetime? No, because it took already energy from another source and then stored that energy, but it is not dissipating that energy like your resistor, but it is storing the energy, but it is giving back energy to the external world. Therefore, it is also passive element, because over infinite time period, what is the amount of energy which is what is given by inductor? Zero, because it has taken some energy, but the same energy is given back. That's why this is called reactive element, but it is not giving energy to the external world. Capacitor, same as your inductor. It is taking the energy and storing the energy, and whenever it needs, again, it is what is giving back to the external world. Therefore, net amount of energy which is what is coming out of these elements is equal to zero. Therefore, resistor, inductor, capacitor, you can call them as passive elements. let us say voltage source, current source, right? People call these two elements as active elements because they are delivering some net amount of energy to the outside world, right? When you purchase the battery from the market, don't take the phase, the fabricating the battery and all, just there is a battery, now that is what is your time t is equal to 0. It is delivering some energy to the outside world, therefore it is what is active element, okay? Then what about PN junction diode? And what about BJT, JFET, MOSFET? People call them as active elements. Means your BJT, PN junction diode, are they giving any external, net amount of energy to the external world? No. But people call them as active elements. Why people call them as active elements? Give me some time, I will clarify that part, okay? But I can say resistor, inductor, capacitor, surely passive elements, okay? Then using passive elements, can we get amplification? There itself is the answer. Using active elements, using transistor, when you keep in the active region, we are getting amplification because BJT is helping you to get amplification. Therefore, indirectly, internally it is not giving any energy, but it is trying to convert the energy from the DC power supply to AC power. That's why people call it as active element, because this is what is delivering to the outside world, because it is processing it. But that processing you cannot get using passive elements, okay? But anyway, I'll clarify that out, just give me some time. But therefore, using passive element, can we get amplification? Based on the definitions, inductor cannot deliver, capacitor cannot deliver, resistor also cannot deliver energy to the outside world. Therefore, passive element, right? Therefore, we cannot get voltage amplification. Then, tell me, what about step-up transformer? If you take step-up transformer, this is what is the choke, let us say, having N1 number of coils, N2 number of coils. Okay, then let us say I am applying the AC signal, let us say this is V1 and I am getting the output voltage V2. Therefore, now tell me what is V2 by V1? V2 by V1 is equal to N2 divided by N1. Let us say N2 by N1 is equal to 100. Therefore, what is the meaning of it? Therefore, what is V2 by V1? This is output voltage and this is what is input voltage. The signal whatever you want to amplify, then if you say 100, then you will get 100 times of your input signal. Therefore, this is nothing but what? V2 is equal to 100 times of your V1. Is it not voltage amplification? If you take step-up transformer, right? This is nothing but voltage amplifier. Because your N2 is greater than N1, let us say N2 is 100 times N1, then I am getting V2 100 times V1. Therefore, this is voltage amplifier, because let us say this is what is my 1 millivolt peak to peak sine wave, then surely I will get 100 millivolt peak to peak using step-up transformer, no doubt about it. You will get 100 millivolt peak to peak divided by 1 millivolt peak to peak, which is nothing but voltage gain of 100. Can't we use this as voltage amplifier? Because we got voltage gain which is 100. But just before I told that for the amplification we need active elements, but this is passive element, but using passive element we are getting voltage amplification. Right? Remember, when I say amplifier, even though I speak about voltage amplification, or I speak about current amplification, or trans conductance amplification, or trans resistance amplification, remember, ultimately all different amplifiers should be supported with power amplification. That is what is very, very important, which is hidden. Normally we will not speak about the power gain, we always speak about voltage gain, current gain, trans conductance gain, trans resistance gain. But remember, it has inherently the power gain, then only we call it as an amplifier. First of all, what is an amplifier? It could be voltage amplifier, current amplifier, trans conductance amplifier, trans resistance amplifier. But the definition of generic amplifier is just first of all take this, then take that also, then I'll tell you what is amplifier. Then from the definition of amplifier, let's see whether your step-up transformer is satisfying the definition of amplifier or not. Definitely it will not satisfy. That's why it is not voltage amplifier, even though we have voltage gain. Okay. First of all take it, then I'll give you the definition of amplifier. Okay. Remember, I have just given some space here because I want to fill it. when you write, you also give some space here, then attenuator, because after explaining something, I'll explain what is that. Therefore, it is easy to remember. Okay, write down.